This time we're going to discuss the next data structure, which is list. List is an ordered collection of data items or data elements. It is a finite sequence of elements and it could be possibly empty. List is a flexible data structure because it can grow and shrink on demand, and elements can be accessed, inserted, or deleted at any position within a list. Now, just like the previous data structures we have discussed, like array, the first one, and then the next is stack, and then the next or the third is queue. List has two basic operations which are common to all data structures. These two are insert and delete, or insertion and deletion. You all know that for array data structure, you can perform insert and delete. And for stack, you can also perform insert and delete, which we call as push for insert and pop for delete. For queue, we also have insertion and deletion operations, which we call for insertion, we call it NQ, and for delete, we call it DQ. So these two basic operations, insert and delete, are available in all data structures. Now, we could implement a list in two ways. First is if we're going to use an array, a one-dimensional array, we call that array implementation, and specifically we call the list a sequential list. If we're going to use pointers to implement this data structure list, we call that linked list. And that's for the pointer implementation. So again, there are two implementations of list. The array implementation, which makes use of a one-dimensional array, and we call that list a sequential list. And if we're going to use pointers, we call that pointer implementation, and we call the list linked list. Now, before we compare the two list implementation, the array implementation and the pointer implementation, let us first review or recall how we do insertion and deletion in the previous three data structures. For array, take note that if this is the one-dimensional array, and say this is element A, B, C, and we have here three elements, say the size of the 1D array is 5. This is index 0, 1, 2, 3, and 4. So say that the capacity of the array is 5. It can hold 5 elements or 5 items. So max number of elements is 5. So initially it is empty, no elements yet. So if you're going to add or insert A as the first element, you position it here at index 0. When you insert after A at the tail of this array, then it will be stored at index 1. So recall that the easiest way to insert a new element and to delete from is at the tail of the array, because you don't need to, or you are not required to, move the elements downwards to make room for a new element to be inserted. Also, you don't need to move the succeeding elements upward so that you close the gap when you delete an element from the array. When you insert, you can insert at any point actually. Like for example, if we have now three elements A, B, C, if you're going to insert a new element D, you can insert at index 0, 1, or 2, or 3, but never 4, because this position 4 at index 4 is not a valid position to insert a new element, because there would be a gap, which is this one, this part here at index 3. Now, that would violate the nature or the characteristic of an array, that there should be no gap. All the elements are contiguously stored in the RAM or in the memory. So the valid position to insert a new element into is only at index 0, index 1, index 2, and index 3. Okay? The easiest way to insert is at index 3 here, because all you have to do is to assign that new element D into that memory location. You are not required to move any of the existing elements. But if you're going to insert at this position, index 2, you need to move C downwards. So C would be here. And so you make this available for the new element D to be inserted. And then that's the only time you can insert D, when you already have moved the existing element C to the next position. If you're going to move at this position at index 0, then there will be 3 elements to be moved. You have to move C downwards, so C is here, B down, and so this would become B, and then A one step down, so this becomes A. So this is now A, B, and C. And so you make this location here available for the new element to be stored, which is D. That's the only time you can insert D. So it is a very tedious task to insert and to delete an element into and from the stack, because you are required to move some elements if you insert or delete at a position which is not the tail of the array. But you are allowed to insert and delete from any valid position. For stack, how do you insert and delete, or how do you push and pop? You are restricted to perform the insert or the push and the pop from only one end. Okay? So only at the top. You cannot insert or delete, you cannot push or pop at the middle part or at the bottom. It is always, you are restricted to perform push and pop only at the top end. While for Q, there is again a restriction, because to perform NQ or insert, you have to do that only at the rear end. That's where you're going to insert or NQ. And for DQ or delete, you can only perform that operation only at the front end. So for stack and for Q, there are restrictions. You cannot delete from any position. You cannot insert at any position. For stack, you have to do these two operations, push and pop, at the top end only. And for Q, you do the delete or the DQ at the front, and for the insertion or NQ, you do it at the rear end. And this time for list, notice that the advantage of list is that you can insert and delete at any position within a list, just like in one-dimensional array. This time, let's compare the two list implementations, which are first the array implementation, which we call as sequential list, and the pointer implementation, which we call as linked list. So since in the array implementation or in a sequential list, we make use of one-dimensional array, that means that in the RAM, the elements of the list as an array are stored in contiguous memory locations. Contiguous means adjacent, there is no gap in between. So like in this case, if this is the array, say the capacity of the array is 1, 2, 3, 4, 5, 6 elements. Say max is equal to 6. So there are 4 elements inside A, B, C, D. The 5th and the 6th position are vacant. So there are only 4 elements. This is the first, A. Second is B. Third is C. And fourth is D. So as you can see in the array implementation, the elements are contiguously stored. There is no gap in between. If this is the first element, the next memory location is where you can find the second element, and the next would be the third element, and the next memory location is the location for the fourth element. There is no gap. And because the memory locations of the elements are contiguously stored, then the elements are easily traversed. How do you do that? In C programming language, for example, or in Java, you could make use of a for loop, like you say, for I from 0, I less than 6, I plus plus. And then inside the loop, every iteration of the for loop, you could access the elements. Say, for example, if the array name is num, so A is num 0, B is num 1, C is num 2, D is num 3. Okay? So you could access num I. You could easily traverse the whole array structure from the first element, starting from the first iteration when I is equal to 0. So on the first iteration when I is equal to 0, this is num0. And that's how you access the first element. When I is incremented, on the second iteration, you access num1. And on the third, you access num2, and so on. So you could easily traverse the elements from the first element to the second to the third in that order up to the last using a loop. For pointer implementation or for linked list, the second characteristic of array implementation or sequential list is that you could easily append or insert at the tail. You could also easily delete, not just insert. You could easily insert and delete at the tail. When you insert or delete at the tail, this is the easiest way to insert and to delete because, as I have already mentioned a while ago, it doesn't require you to move any elements upwards or downwards. Okay? Like if you're going to insert here another element E, then you could just assign num4 to E, to the value of E. Okay? You don't need to move any of the existing elements A to D. The problem is when you are going to insert somewhere in the middle, and worst is at the first position of the array, which is A, inserting here, because that is the position where the most number of elements are moved. To delete is also easiest at the tail, right? Because if you're going to delete, for example, letter D, all you have to do is to decrement the size of the array or the list. So currently the size is equal to 4 because there are 4 elements A, B, C, D. When you decrement it, then this becomes 3. And although you don't necessarily would say num3 gets blank, okay, just to erase letter D, you don't have to do this because the main reference for the list elements is the size. So from the first element, the size is 3. You count 1, 2, 3. And so these 3 elements are considered as the only elements in the list. D is no longer counted, although the value D is still there inside the memory location. But since it is no longer referenced, then that is considered as not included in the array. The third characteristic of array implementation or sequential list is that you are required to move or shift succeeding elements during insertion and deletion in order to make room for new element. That is when you're going to insert, or to close a gap when you perform deletion, just like what I have already described to you last time. So these are the 3 characteristics of array implementation or sequential list. So again, we have in here a list containing elements A, B, C, D. The left side is array implementation. So we call this a sequential list of 4 elements A, B, C, D. And on the right side is the same list with elements A, B, C, D, but we make use of pointer implementation, and so we call it a linked list. For the pointer implementation or linked list, the first characteristic is that elements may not be stored in contiguous memory locations. So as you can see here in the sequential list on the left side, the array implementation, that the elements A, B, C, D are contiguously stored in the RAM, or the 4 elements are stored in contiguous memory locations. While for linked list, the elements may not be contiguously stored. For linked list, one node represents one element. What is a node? A node is like a class type having two fields. So it has two parts or values, the element value itself, and the second is the link or the pointer to the next element. And recall how we define pointer in our previous programming subject. A pointer is simply a memory address. So the first value of the node is the element value itself, and the second value is the memory address of the next element. So we could think of a node as this one here. This is one node. The first node is containing element A. So this has two parts. This is A, and the second value is a pointer to the next element. So this is like a link pointing to the next node. This is another node that holds the value of the next element, which is B. And then the second part of this node is a link or a pointer to the next node holding the next element C. And then this one points to the next node, which holds the value of D. Okay, so this first node here holds A, the first element. The second node here holds element B, the second element. And the third node holds the third element C. And the fourth node, which is this, holds the fourth element D. And each of this here is a pointer to the next element. Now D is the last element, so the pointer here is null, or in Python, that is simply none. Null in Java or in C, and none for Python programming language. This is now what we call our linked list. The linked list is this one, okay? Consisting of 4 nodes. First node, second, third, and fourth node. And in the RAM, this linked list is, say for example, this linked list is stored, say for example, this way. Since each node has 2 parts, and say this first part here being a character, that's one character. Remember that it is 1 byte in the RAM. So this is 1 byte. The first part of the node is 1 byte. The second part of the node is another byte, for example. So one node is allocated 2 bytes. The first byte is containing the first element value, and the second byte is the pointer value. So say this is node 2, these 2 bytes here, and the next node is for node 4, and the next 2 nodes. And take note that this may not be contiguous, so there may be many more memory locations in between in this part here, the ellipsis. Okay, so there could be many more memory locations there. Say this is memory address 85, so this is 86, and say this is 91, 92, and these are 126, and this is 127. So say this is your node 1, and these 2 here are for node 3. So the ellipsis here, these 3 dots here, the ellipsis represents many more memory locations in between. And in here, also here, there could be several memory locations. Node 1 is containing A, so the first byte is A, and the second is the pointer or the memory address of B. What is the memory address of B? B is node 2. So this is node 2, B, and node 3 is C, and node 4 is element D. Okay? So the value in here is the memory address of B, which is 72. So the value here is 72. Now 72 is not an ordinary integer value. It is a pointer, or it is a memory address referring to this memory address 72. So the meaning of this 72 here is to be able to locate the next element, and the location of the next element after A is at 72, memory address 72. So when you go to memory address 72, there you have element B, which is the second element in the list after A. And so the value in here, the pointer value after B, would be the pointer or the memory address of C, which is 126. 126 is the memory address, which is this, of the next element C. And so the value in here is the memory address of D, which is 85. 85. So this is 85. 85 is the memory address of the next element after C, which is D. And in here, we have null. Okay, so the value in here is not any of the valid memory addresses, since that is null, meaning it doesn't point anywhere because element D is the last element. Okay, there is no next element after D, so the pointer here is null. So take note that for pointer implementation or linked list, the elements may not be stored in contiguous memory locations. As you can find here, at memory location 91, you have the first element A, and the second element is B, which is at address 72. And the next element after B, the third one, is at memory address 126. And after letter C, the fourth element in the list is letter D, which is found at memory location 85. So in a linked list, or in the pointer implementation for list, the elements may be randomly stored in the RAM. They are not necessarily contiguous, just like in the sequential list or in the array implementation. Now let's take a look at the total bytes memory allocation for array implementation for this sequential list ABCD. How many bytes are allocated or consumed or used by the sequential list ABCD? That would be 4 elements times 1 byte each. So the total is 4 bytes. Okay, so currently now it has 4 elements ABCD. It consumes 4 bytes of RAM space. How about for the linked list ABCD? If we implement this list ABCD as a linked list, how many total bytes are allocated? There are 4 nodes, right? For 4 elements, times each node is occupying 2 bytes. So that would be 8 bytes. So the total RAM allocation for sequential list ABCD is 4 bytes. And for linked list ABCD, it is 8 bytes. So the RAM allocation here for pointer implementation or linked list, RAM allocation is doubled. This is 8 bytes, while this one here is just 4 bytes. 4 bytes against 8 bytes. So the RAM allocation for linked list is doubled. That's why in here, number 3, it says requires extra memory space to store pointers. Okay, so it requires extra space to store the pointers. So how many pointers are to be stored? It is equal to the number of elements, because each element has a pair pointer. Okay, in the node, each element has a pair pointer. Element, pointer, element, pointer, element, pointer. And we consider this characteristic of linked list or pointer implementation as a disadvantage because, of course, remember, in good programming practice, you are to save memory spaces. But the advantage is that you may not store the elements in contiguous memory location, and the biggest advantage of linked list or pointer implementation over array implementation or sequential list is that Second point, no more moving or shifting of succeeding elements during insertion and deletion. Why is that? You don't need to move elements anymore. When you perform insertion, for example, in linked list, when you perform insertion in linked list, say this one here, this is our linked list for elements A, B, C, and D. If we're going to insert, say at this position, we're going to insert a new node containing element E. So we want the linked list to become A, E, B, C, and D. We want to insert a new element E at the position of B. And so if this is a sequential or array implementation list, you need to move D to the right, and then C to the right, and then B to the right. So you move all of this, and that is a tedious task, and it would mean longer running time. But for linked list, when you're going to insert a new node at position B, then you just have to create this node and set the element value here to E, and then make this pointer to point to E. How do you do that? By saying, for example, this is called, say the first node is called list2. Say we define the two fields of class node is element. Say this is character. And then the type of the next, say it is link. The name of the field is link. The type is a node pointer. Say we call this list2. So all you have to do is to create a new node. Say we call this new node. How do you do that in Python? You would say new node is an instance of node, and then you say new node dot element is equal to E, the new element, and new node dot link is equal to, where do you want this to point? You're going to make it to point to B. So you would say this would be gets, we call this node list2 dot link. List2 dot element is A. List2 dot link is this one. And wherever this is pointing, it's pointing there. Okay, it's not pointing this here yet. Okay, so let's remove that. So new node dot link, this is new node dot element is E. This is the element part, and this is the link part, element, link, element, and link. So you say new node dot link, referring to this here, gets list2 dot link, or it points to where list2 is pointing. List2 is pointing here, so this one would be pointing there also. What is the value of list2 dot link? It is 72, right? This is 72. And so since this is 72, if that is 72, this would also be 72, meaning this would point to that node located at 72, which is B, node 2. And then you make this to point here. How do you do that? You would say list2 dot link gets new node. So new node is this node. You cut this one, you make this to point here. So list2 dot link, which is this one, now points to new node. So what is the result? From the first node A, it points to this as the second node now, and this one points there, so this becomes now the third node, and this becomes the fourth node, the fifth node. So now we have element A first, next is E, next is B, next is C, and next is D. So we have inserted new element E at the previous position of B, or the second position in the list. And did we move B and C and D forwards? No, we did not. We could just, if this part here is new node, these 2 bytes here is a new node, you assign their E by this statement, and then by this statement, you make these 2 have a value 72, which means that it is now pointing on node 2, right? And you make list2.link, which is this one, to get the address of new node, which is, say for example, this is 150, memory address 150, and this is 151. So this becomes, the value here becomes 150, because that is the memory address of new node 150. So from first element A, the next element is located at 150, which is here. So this is now the second node. This is now the node 2, this is the node 3, this is the node 4, and this is the node 5. So we did not move or shift any element during the insertion, and that's also true for deletion. So say for example, if we're going to perform deletion, okay, say we erase all of this. Let's get back to the original list, the ABC. So this one is pointing there. So from A, this pointer points to B, and B points to C, and C points to D. Say this is the original linked list. If we're going to delete this node, all we have to do is to say list2.link, which is referring to this one, gets or points to where this one is pointing. What do we call to this pointer? It is called list2.link.link. List2.link, this one here, refers to this, and since that is say 72 and this is 72, that is node of B. So this list2.link refers to this node, node 2. And then you say that link of that. So this is, you are now referring to this pointer. So the first pointer is list2.link. The second pointer is list2.link.link. This third pointer is called list2.link.link.link. Okay, list2.link is this one. List2.link.link is this one. And so the dot link of that is this one. So list2.link, which is this, points to where this is pointing. So list2.link, which is this one, points to where this is pointing. This is pointing to that. So it will just point there. Okay, this is now your list2.link. Instead of pointing there, that is cut, and now it points there. So starting from the first element A, when you trace the pointer or the links, it now points here as the second node or the second element. And this one points there, so D is the third element. Now we only have elements A, C, and D. We have deleted B. And take note that when we delete B, we did not move or shift all the other elements. It takes only one statement to do that, and that is to redirect this pointer to point on the third node. So what happens in the RAM? Your A is now set to, what is the address of C? It is set to 126. So in here, from 72, the value of this pointer now becomes the address of letter C, which is 126. to 6. So from A, go to 126, that is C, and then go to 85, that is D, and then null. So we now have only A as the first element, C as the second element, and D as the third element. And that's in that way we have deleted element B from the list.